So we're looking at section 1.2 today, which is use segments and congruence. So we have a couple vocabulary terms to get out of the way first. Our first one is this rule that in geometry, a rule that is accepted without proof is called a postulate or axiom. So these are things that are super obvious. A rule that can be proved is called a theorem, and we're going to see those later. So our first postulate here is the ruler postulate, and it says that the points on a line can be matched one-to-one with the real numbers. The real number that corresponds to a point is the coordinate of the point. So we have this diagram here, and it's just showing the points, and these are the coordinates x sub 1, x sub 2. Then we have that the distance between points A and B, written as AB, is the absolute value of the difference of the coordinates of A and B. So notice there's no line above this or anything. That distance between a segment is just AB, and it's written as that absolute value of whatever your x2 is minus your x1. So in the diagrams above, the small numbers in the coordinates x sub 1 and x sub 2 are called subscripts. And as I've been reading, they're called x sub 1, x sub 2. They're not an operation. It's not being squared or anything. The distance between points A and B, or that AB, is also called the length of that segment AB. So our first example here, we just have this ruler postulate, and it says measure the length of ST to the nearest tenth of a centimeter using that ruler given. So the first thing you want to do is you want to name what's T at and what's S at. So S is pretty obvious. This is at 2. T is a little trickier. It looks like it's at about 5.4. So to find the distance here, we would say that ST is equal to the absolute value of 5.4 minus 2, which in this case is 3.4. The reason we have those absolute values is just because it doesn't make sense to have a negative distance in case that happened. Then we have adding segment lengths. So when 3 points are collinear, you can say that one point is between the other two. So point B is between points A and C, and point E is not between points D and F there. We have this second postulate, which is our segment addition postulate, and this is one of the big ones. It just says that if you have a point B that's between A and C, then you can add AB, so this length here, plus BC to get your total length, which makes sense. We're going to do this a lot, and sometimes we're going to have some algebraic expressions in there. So this first example, or second example, is apply the segment addition postulate. So we have the cities shown on the map lie approximately in a straight line, and we're going to use the distances to find the distance from Lubbock, Texas, this right here, to St. Louis, Missouri. We know the distance between Lubbock and Tulsa, and between Tulsa and St. Louis. So we could say that LT is equal to 380, and TS is equal to 360. So we know then that LS is equal to LT plus TS, and then you just substitute in. So LS equals 380 plus 360. So that distance is 740, in this case it'd be miles. So this part here where you set it up is pretty important for later examples where they get a little trickier. So this is more student practice for you if you would like it. Now we're going to do another, this is one now where we have the total and we have one segment and we want the other segment. So again, it's important to say, okay, my total, FH, is equal to each part, so FG plus GH. And then you substitute in what you know. FH is 36, FG is 21, and I don't know my GH. So to find it, now this just becomes an algebra problem, and I just subtract 21 from both sides. So I get that 15 is equal to GH. Here's another example with some algebraic terms. So this doesn't give us the picture, so it's important that we draw the picture first. We have this line. It says point S is between R and T on RT. So draw R and draw T, and then we have a point S in between. Now we're going to fill in what we know. So RS is 2x plus 10. ST is x minus 4. And then we know that this total is 21. So it's important that we set up an equation. We have the total equal to the two parts. And then we can substitute in our values. So RT, we said was 21. RS is 2x plus 10. And ST is x minus 4. So when I add these together, I have 3x plus 6. Subtract 6 from both sides. So let's see here, 21 minus 6, it's 15. Equals 3x. Divide by 3 on both sides. So that's gone, and we have that x equals 5. Now, we have to be careful. This actually didn't want us to just find x. It wanted us to find RS and ST. So in this case, RS is equal to 2, and then instead of x, I'm going to put 5 plus 10. So 2 times 5 is 10, and 10 plus 10 is 20. So RS is 20. And then it wanted us to find ST, and again, we just plug in 5 for x, so we have 5 minus 4, so ST equals 1. So this problem's a little trickier. More student practice for you. Here we have comparing segments for congruence, so we just want to see if these are equal to each other. They give us the coordinate points, and we can actually just count it out here. So we can see that JK is equal to 1, 2, 3, 4, 5. And LM is equal to 1, 2, 3, 4, 5. So we would say that these are congruent. So we could say JK, and now we're going to use the segment, is congruent to LM. So this little symbol is our congruent symbol. And this is when we're comparing like geometric figures, like a line segment or a plane, and not an actual number. We would say it's congruent instead of equal, but basically they're the same thing. So congruent is equal for segments when we're just comparing the segments. And we'll use that a lot. So the rest of this is all student practice. So you can kind of go through this, and then we will touch base on this next week.